So welcome back. This is a little bit of a parenthesized lecture that is not a new technology or anything. It's just that I would like to step back, take a little break, and look at considerations about performance at large scales, right? So I already talked a little bit about pushdowns, optimizations, about data frames that basically occupy much less space in memory and on disk. But I'd like to take some time in order to explain that, right? So you can already see everything we've covered. It's already a very large part of the stack. And so basically, if you start using a system and you start using a lot more data and a lot more complex data, then many people start experiencing that at some point it might slow down, right? So it takes an hour instead of taking 10 minutes, and then it becomes impracticable. And this is the point at which you have to ask yourself, can I optimize in any way, right? So normally, a very well-designed system that is data independent should figure a lot of things out, right? So even if you write a query that's not very efficient, a very good database system will still be able to optimize on its own. But as you might know, the problem of optimizing is undecidable. So there's no way that we are going to have a perfectly data independent database system that figures out absolutely everything, understands everything you want to do, and figures out the best way of executing that. That is an impossible problem. We can improve every year, build better and better and better systems, but we still need the human to look a little bit into it. And so you might have sometimes, even though you wrote maybe a very good query, to start looking into the details and figure out what is slowing down the system. And this is where the knowledge is useful. So I'm giving you a bit some high-level knowledge here of tricks, tips and tricks. So first, the idea of bottleneck, which is usually what's causing the slowdown in the system, is the idea that it's basically this image right here, that some parts of the systems are not fully used, and then some part of the system is completely saturated, and then not fully used again. Well, I'm not a hardware person. There are sufficient numbers of professors and lecturers who can teach you about hardware. As a database person, I look at hardware from a bit of an abstract perspective, so I kind of understand that there's some memory which, when you shut down the electricity, it's gone. I understand that there's CPU that processes things and that calculates things. I understand that there are disks that persist the data over the longer term, even when the electricity is gone, it's still there, so it's durable and persistent. I understand that there are cables connecting the machines and that you can use to send the data over the machines, typically when you shuffle the data over the network. And so the idea of the bottlenecks is that when your system is slow, it's always the case that one of them is the bottleneck. One of them, always one. So it could be that it's the CPU. So you notice when you log on to the activity monitor and you realize the CPU is at 100%, right? Or it could be the disk. The disk is reading at maximum speed like crazy at maximum throughput, and you cannot do faster than that. Or it could be that it's the memory. Your memory is absolutely completely full, and it starts swapping and moving between disk and memory because you don't have any space anymore. Or it could be the network cables. You're at the maximum network bandwidth, and that doesn't go any faster than that. So the first thing you need to do when your system is slow, you need to find out which one of the four it is. Right? That's the very practical high-level advice. First, figure that out. And here you need some sysadmin or SRE skills. So you really need to connect yourself to some internal interfaces of the system and see where your bottleneck is. This is rule number one. If you try to optimize something, but it's not the bottleneck, you're wasting your time, right? For example, if the bottleneck is the memory and you try to write better code, that's not going to help because the bottleneck is in the memory, right? For whom is that clear? Right? So this is the first high-level piece of advice. Always start figuring out where your bottleneck is, right? So now, the disk bottleneck is particularly relevant for big data because MapReduce and Spark were designed to solve the disk bottleneck. So if you're trying to analyze your data on your laptop and the disk is completely overloaded and overwhelmed, then MapReduce and Spark are for you, right? So this is exactly what Spark and MapReduce were designed for, because you parallelize reading from the disk, right? That's very important to understand, right? So now, in order to make your measurements, you need to understand the notion of latency, right? So when are you waiting for data? It could be network latency, it could be disk latency. I already showed you the prefixes, so that you need to know, because sometimes you need to do some mental calculus or estimate orders of magnitudes. Who knows the prefixes now? Right? I didn't even push with the Rona and the Queta here, right? But you need to know the prefixes. Here are the negative prefixes, the negative powers of 10. Who knows them all already? Okay, who knows the first four? Right, these are the ones you need to know. We are not yet, maybe some quantum physicists are in the femto, atto, and so on, but the first four you need to know, right? So here, it's a good idea to have some high-level notion of, for example, the time it takes when you're within the CPU. Technically, you're speaking about nanoseconds. And when you start getting away from the CPU, you go into the microseconds and then milliseconds, right? So you should know a little bit the order of magnitudes that things are taking, right? So for example, when you're really inside the CPU, it's nanoseconds. When you're over the network very locally, or the memory, it can be microseconds. As soon as the disk is involved, then you get into the milliseconds, right? That's because of some latency that there is. And of course, if you ship something over the Atlantic Ocean, which is then a completely different zone, then you're already at the hundreds of milliseconds. So it's a very good idea to have in your mind, by heart almost, these orders of magnitudes, because that can help you to understand your bottlenecks, right? For example, if you're wondering why it takes 100 milliseconds to do a database lookup instead of just 2 milliseconds, well, if the database is in the US and you're querying it from Europe, then you know why. That's because the time it takes over the Atlantic Ocean. Right? So it's important to basically know these orders of magnitudes. Then on the transmission of data, the state of the art in data centers now, I think, is mostly 200, 400 gigabit per second in the local network cables. And now the industry is going into the 800 or 1600 gigabit per second technology, right? 1 gigabit per second is typically what you have at home when you connect maybe 10 gigabits now for some providers, right? So it's also good to have an idea here. Why? Because when you shuffle the data, you can do quick calculations on the estimate that it takes to shuffle the entire data or an entire block over the network. That gives you quick estimates of the time it takes to download. The HDD, so the hard drives, counts maybe around 100 megabytes per second to read from the disk. The SSDs are faster, and there's a range. Some of them start at 500. The newest one that I showed you, the enormous disk at the beginning of the lecture, goes to 12,000. That's really the high end, right? That's very untypical for disks. So maybe more typical would be 3 or 4 terabytes per second, right? For good SSDs today. So it's good to have these orders of magnitude in order to have expectations on what to expect with the bottleneck, right? So now, when you have a system and you measure things or you try to understand, there is the latency until you start receiving the first bit of data. But some other people look at it differently, and they use latency for something else, for the total response time between the hitting the return button and having the last bit of data downloaded to you. So here we'll call it the total response time, right? So this is a lot of PhD students have to deal with these things when they plot their data for conferences. So they try to measure end to end with what's going on, right? Okay, that I think I would just jump over it. I wanted to remove a few slides because we spend more time on some new aspects to adapt to questions. So I always try to compensate by dropping other things. All right. So now I'm repeating something you already know. You can scale out by adding more machines. You can scale up by having bigger machines, right? So maybe if the memory is not enough, you can try to add memory to the machines. But you really need to remember what I already told you, that this should be a last resort, right? So before you add more machines or before you increase the cores, the memory, and so on, first try to figure out if you cannot write more efficient code. Can you use data frames instead of RDDs? Can you use Parquet instead of a JSON lines file, and so on? All of these sort of things, right? So when you scale up, you have to first figure out how to avoid scaling up in the first place. So let me give you a few examples for the memory. How can you optimize memory? Because you might have classes in Java. If you're a data engineer and you implement some complex codes with Spark in Java, you might have an object in your class that is instantiated billions of times. So what you need to do is look very closely at your class definition. Is there any field that you don't need? Can you drop it? Can you use more efficient types? So it's really the time to look at those classes that are instantiated billions of times. Maybe you're storing things redundantly, so you need to chase for stuff that might be redundant to avoid that. And finally, you can avoid inheritance because that adds some more place in memory when you use inheritance. So you can try to be lean and to avoid any inheritance, right? So just flat class hierarchies can be very useful. So these are some of the tricks that especially at firms like Google or people who write code that executes billions of times. That's kind of the mindset. Right? So that's for the memory. I'm stopping here for today. I'll continue tomorrow on some of on the other aspects of avoiding the scale up. Thank you very much for attending today's class, and I'll see you tomorrow on more tips and tricks for performance. Thank you.